Okay, so it's our great pleasure and incredible honor to have Professor Shanhui Fan today from Stanford University. Shanhui Fan is a professor of electrical engineering, a professor of applied physics by courtesy, a senior fellow of the Precourt Institute for Energy, and the director of the Edward L. Ginzton Laboratory at Stanford University. He received his PhD in 1997 in theoretical condensed matter physics from MIT. His research interests are in fundamental studies of solid state and photonic structures and devices, especially photonic crystals, plasmonics, and metamaterials, and applications of these structures in energy and information technology applications. He has published over 550 refereed journal articles, has given over 350 plenary keynote invited talks, and was granted 62 US patents. Professor Fan received an NSF Career Award, a Packard Fellowship in Science and Engineering, the National Academy of Sciences W.O. Baker Award for Initiative in Research, the Adolph Lomb Medal from the Optical Society of America, and a Vannevar Bush Faculty Fellowship from the US Department of Defense. He is a Thomson Reuters highly cited researcher in physics since 2015, and a fellow of the IEEE, the American Physical Society, the Optical Society of America, and the SPIE. So whenever you're ready, it's our great pleasure.
Well, thank you, Judith, and thanks for the very kind introduction. It's a great pleasure to be here. So I would like to talk about some of our recent work in doing computing with photonic structures. As a background, these days, there's certainly a lot of interest in machine learning, and the computing requirement for machine learning are increasing exponentially. And that in turn has motivated very significant investment in hardware that are specialized for machine learning. And you see that in the electronic side in terms of development of GPU, TPU, as well as the development of a wide variety of neuromorphic computing platforms. Optics certainly could be very interesting in this context as well. Here is one of the standard model for machine learning, the artificial neural network or the deep neural network. And this is widely used to find complex features in data. And the one of the canonical problem that people usually talk about is this hand digit recognition problem, where you take an image of a handwritten digit and you will want to recognize what is being written. And this is solved by passing the image into a artificial neural network that look somewhat like what I'm drawing here on the right. So the algorithm that's required involve a linear transformation of the image, and this is a linear, so it's a matrix vector multiplication, followed by an element-wise nonlinear activation function, and then the process repeats. So the dominant computational cost in these artificial neural network calculation is the matrix vector multiplication. And this is where optics actually has an interesting opportunity. If you take any linear optic structure, you pass light to it, then the input-output relation, being a linear system, is described by a matrix vector multiplication. So, for example, if you take an array of waveguides and you form Mach-Zehnder interferometer meshes, then the input vector would be the amplitude in each of these waveguides, and the output will be the amplitude on each of these waveguides, and these amplitudes are related, excuse me, by the transmission matrix of the system. Similarly, if you have a matter surface, you send in an electric field distribution on one side, you look at the electric field distribution on the other side, and they again is related by linear transformation described by matrix. So in optics, actually, routinely, you do matrix vector multiplication all the time. From a computing point of view, there's actually a lot of interesting aspect about using optics to perform matrix vector multiplication. First of all, in terms of speed, the time that it takes is the propagation time. And so in optics, even if you propagate over a millimeter distance, the time is still on the order of a picosecond. And this is in contrast to digital computation, where the switching time, the clock rate, is probably on the order of 0.1 nanosecond. Also in optics, the matrix vector multiplication is done in an entirely parallel fashion. It's largely independent of the size of the vector. Whereas in digital computation, this scales as n squared, where n is the size of vector. And finally, in optics, the matrix vector multiplication is done passively. There's no additional power in principle that's required other than the power in the original optical signal. In digital computation, you're talking about an active device, so that does cost energy. So certainly there's a lot of interesting, very interesting aspects of using optics to perform matrix vector multiplication. And this is also not a new idea. It shouldn't be, because this is what optics is in matrix vector multiplication. So in fact, has been really thought about for a very long time. But as you know, it really has not taken off. And so there are a long list of issues that you can certainly think about using optics to do matrix vector multiplication. And here I just brought up one. One of the issue is, of course, accuracy. If you do optics this way, you're computing with optics this way, you are doing analog computing. And the kind of accuracy that you can get is nowhere near what you can do with digital computing. So if somebody asks you to build a interferometer and to compute these things, let's say to 16 digits and so on, I think you would know you're out of luck. Now, neural network, many of the computing though, actually may not need high accuracy. The point of the memory neural network computation is to try to capture the essential broad scope feature of a particular signal. And in those cases, the key point was to capture these features, and the high accuracy may not even be essential. So this provides a very interesting opportunity to relook at using optics to do these computations. So with that as a background, here's a brief outline of my talk. I would talk first about a very simple calculation that optics can do, and that's potentially useful for image processing as well, and that's called edge detection. Then I'm going to go into talking more about using optics to implement neural network algorithms. So let me start with the first part. In an edge detection, what you would like to do is to take an image, for example, this Stanford tree logo, and generate an output image that highlight only the edge. So mathematically, you can do this by perform a differentiation operation on the input image. Edge detection is actually very important in image processing, and it is, for example, of fundamental importance in human visual system. After an image has been formed on the retina, the neural network in every one of us immediately perform an edge detection step before sending the resulting, and then send the resulting information back into the brain for further processing. So it's a first step in human visual system. Similarly, it is also a very important step in computer vision. The reason that edge detection is important is that it significantly reduces the amount of data that need to be processed. It filters out irrelevant information and preserves those important geometric features that are important for recognition purposes. And in the human visual system, this is important because you probably would know that the bit rate in a typical nerve is very, very low. We're talking about probably millisecond pulses and so on. So the amount of bits that one can send from the eye back into the brain is not that much for processing purposes. So, and this in fact arises for many other situations where edge detection is important as well. So even though edge detection by differentiation is a simple mathematical operation, it is in fact interesting to be able to do that directly in the optical domain if high throughput, for example, video recognition is necessary in some of the applications. Using optics, so therefore there's an interest in doing edge detection optically, and this has a long history. You can do that with Fourier optics. So what you do is you use a lens to do a Fourier transformation on the input beam, and then you put a mask in the focal plane. This essentially allows you to do a wave vector space transformation. And then after transformation, you transform them back out. And with the right choice of the mask on the focal plane, you can generate the UI output and to do differentiation. The problem with this is that it's a fairly bulky system. In recent years, there have been quite a bit of interest in trying to develop a matter surface structure. These are compact thin film structure to do differentiation optically. And one of the influential paper is by Angat and Lu group, who proposed a matter surface structure, a reasonably complex one to do one-dimensional differentiation. So what I like to show here are set of work where we're trying to push along this direction. And so the first work I'm going to show is an experimental work where we provide a very simple geometry to demonstrate one-dimensional differentiation in a compact nanophotonic structure. So what we're going to show is that we can use surface-plasmon actually for differentiation purposes. And the setup consists of just a thin gold film of tens of nanometer put on a prism. And what we show is that by choosing the thickness of the gold film correctly, the reflected light, in fact, is a differentiation of the input light. So this geometry is commonly referred to as a Kretschmann geometry. It's a standard geometry to excite surface plasmon. And when you have light that's incident onto the metal film, there are two reflection pathways. It can be directly reflected from the bottom mirror, the bottom surface, or it can excite the surface plasmon on the metal air surface on the top surface, and the surface plasmon then leaks back. The interference of these two pathways determine the total reflection coefficient. So when the surface plasmon is excited at a particular angle of incidence, you will see a dip in the reflectivity. And since this is an interference process, if you were to choose the thickness of the gold film appropriately, then at the angle where you excite surface plasmon, the reflectivity can go to 0 and light is completely absorbed. In the vicinity of this angle, if you look at the reflection coefficient, the amplitude reflection coefficient as a functional wave vector, it varies linearly as a functional wave vector. And if you remember your Fourier transformation class that you took, this is a one-dimensional spatial differentiation if you transform this back into a spatial domain. So consequently, with this setup, if you send in an image and look at the reflection, the reflected image should be a differentiation of the input image. And for example, here's a test where we put in these square apertures. So light pass through the square and into the setup. And in the output, you can see the edge of the, these are not square rectangles, the edge of the rectangle lights up. It's one-dimensional differentiation, so we're differentiating only along this direction. So only these edges lights up. And from this, you can also define a spatial resolution of the differentiator. So if the two edges are far apart from each other, you can see they're very well resolved in the output image. If you put them very close, at some point they merge together. And the resolution determined this way is about 7.5 micron, which I think is probably quite sufficient for most of the image processing tasks. This is a coherent light image differentiation. So it detects edges both in amplitude and phase distribution. As a demonstration, on the top here, we have the one image where the intensity inside and outside the logo are different. And you can see the output image lights up the edge. In the bottom here, we have a situation where the intensity inside and outside the Stanford logo are the same, but the phase differ by pi. In this case, in spite of the absence of contrast in the intensity in the input image, the output image detects the phase contrast, and you can see the edges also light up in this output generation. So now I've shown you that one can do one-dimensional edge detection. For many image processing tasks, you would like to be able to do two-dimensional edge detection. So if you take an image like that, you would like to be able to highlight the edge independent of the orientation of the edge. One way to do that in image processing is to apply a Laplacian operator of the input image. And this provides you a way to do isotropic differentiation. And so it's widely used for edge detection purposes. If you do a Fourier transform, the Laplacian can then transform into kx squared plus ky squared, where these are the in-plane wave vectors. So one thing that you see immediately is that in terms of the transfer coefficient, what you would like is at the center beam of the image correspond to kx and ky equal to 0, the transfer coefficient need to go to 0. So in other words, what you like, at the very least, if you want to get a differentiation, is to get a 0 in the transfer coefficient. And this actually, there are many ways to do so. One way that connected to a very old work that we've done in photonic crystal was that if you take a photonic crystal, let's say a thin film of silicon that about a few hundred nanometers thick, and you put in a periodic array of holes with the periodicity comparable, but usually a bit smaller by a factor of 2 or 3 compared to the free space wavelength, then you have a photonic crystal. And if you have light coming in from the normal direction, the periodic index contrast here can phase match the input light to the guided mode inside the photonic crystal. And then that guided mode and leaks out, create a guided resonance. So consequently, if you look at the transmission spectrum, you will have frequencies where the transmission really go to 0 at the normal instance. And that, of course, is the 0 that we are going to use for differentiation purpose. So at normal instance, the transmission go to 0. And what you would like to do is that if you operate at that frequency, you now consider a k not equal to 0 correspond to off normal instance. Then you would like to have some non-zero transmission. You run the transmission coefficient to vary quadratically as a function of k. And so the 0 here corresponds to guided resonance. So therefore, when you move away from k equal to 0, the guided resonance will trace out the band structure. And suppose you have a band structure that is quadratic, which is typical, and moreover, the curvature is the same as you change the direction of k, then you, in other words, then you have an isotropic band structure, then you will have a transmission coefficient that scales as k squared in an isotropic fashion. And in doing so, therefore, you can implement a Laplacian. So it turned out that this idea takes some amount of work in terms of design, because if you take a regular photonic crystal, let's say this square lattice of air holes, it turned out that due to the spin-orbit coupling, the generic band structure near k to 0 is in fact not isotropic at all. Here's a plot plotting omega as a function of k along 2 different directions, and you can see the curvature is quite different. On the other hand, if you work hard at it by really choosing the parameter correctly, then you can get isotropic band structure. Here's the constant frequency contour of these bands, and you can see they look like circle in the kx and ky space. And when this happens, if you compute the transmission coefficient at the frequency of the band edge as a function of in-plane wave vector, and here is a constant, there is a constant transmission coefficient plot as a function of wave vector, you see that the contour here are all circle, and that gives you an isotropic transmission. And with this, one then can implement Laplacian. So here is the numerical result where you take input image like the Stanford tree here, and here is the output image. You can see all the edge lights up. And also, in fact, as a fun fact, you can see this is a Laplacian by noticing that all the corner here lights up more because the derivative really highlight the corner more than the edge. So it take a regular Stanford tree into a tree that look like a Christmas tree, which is, I think, probably appropriate for this time of the year. So this is something that you can do numerically. And there has been a very nice experimental demonstration from Jason Valentine's group in Vanderbilt, demonstrating that you can indeed use these kind of photonic crystal slab to perform 2-dimensional differentiation. In spite of this differentiation, the demonstration, there's in fact some issues associated with this design. And as I mentioned, to make it work, you really have to design the structure very accurately. So it requires detailed structure tuning. And also, the transmission coefficient in this case is 0, a normal instance only at a particular frequency, and that's the frequency that you need to operate in. So therefore, the bandwidth that you can operate is relatively narrow. So to overcome these limitations, we recently done an experiment to try to do a more robust broadband two-dimensional spatial differentiation, and that requires a little bit of use of topology. So first, let's again review the transfer function associated with the Laplacian. And this is the mathematical form. And you can plot it. And it has a 0 at the center. And then it's quadratic as k move away from 0. And the phase of the transfer function is uniform. It's in fact a real transfer function. Now, from a topological point of view, this kind of 0 is in fact non-robust in the sense that a small perturbation would easily remove them. This is in contrast to a topologically non-trivial transfer function. And so if instead you take a look at a first order differentiation operator that indicated here, and you look at its spatial, the Fourier domain transfer function, in this case, again, you get a 0 at k equals 0. But instead of a quadratic line, now you have a linear line. And also around the 0, this function here, if you go around the 0 by one circle, the phase of the transfer function vary by 2 pi. So therefore, there is a non-trivial phase winding, and that guarantees that this 0 here is topologically robust in the sense that a small perturbation cannot easily remove it. So therefore, if one could design a structure that gives you these kind of transfer function, you will have a spatial differentiator that is topologically robust to demonstrate. So it is in fact fairly straightforward to come up with these kind of transfer function. You take any dielectric surface, you send in an input light with a particular polarization, and at a particular angle of incidence, the reflected light will have a particular polarization as well. And you can choose the setup so that there will be some polarization conversion. Now, with this, suppose you put in a polarizer to select a polarization direction that's perpendicular to this output polarization here, then for this particular ray, the reflection coefficient is 0. And therefore, you have created 0 in the wave vector space. Away from this direction, so you have a nearby beam with a slightly different direction, typically the output polarization that's going to be coming out will be slightly different, and therefore the polarization will allow some of the light to pass through, and therefore you can generate an isolated 0 in the wave vector space. So in doing so, by choosing the input polarizer in the correct way, you can create such an isotropic differentiation function, and which in fact is also a generator of an orbital angular momentum. So to summarize, the setup that we do is we basically just take a dielectric surface, we have a reflection, and we have an input polarizer and output polarizer. And we select the input polarizer in the right way to create basically an isotropic differentiation transfer function. So there are many ways to do so. Here's a particularly simple way. If you just take a look at the dielectric air interface, there's a Brewster angle. So the p-polarized light would not be reflected at all. So at that angle, if you choose the output polarizer to select the p-polarized light, then there won't be any reflection. Now for this, if you choose the input polarization correctly, and you look at the transfer function as a function of kx and ky, you will have a 0 at the center, correspond to the Brewster angle, and an isotropic deviation from 0 as you move away from the center. And this, even though you cannot see in this intensity plot, this is a measurement result, you can get the phase distribution by an interference experiment where you take a Gaussian beam and you take the reflection, and then you interfere the reflection with part of the Gaussian beam that you directed elsewhere. And in doing so, the interference pattern, which is indicated here, has this very characteristic winding pattern that tell you the 2 pi phase winding in the system. So this, in fact, generates a orbital angular momentum beam. So this experiment that I show you, if you put in an input Gaussian beam, the output beam looks like a donut in the intensity profile with a 0 at the center, and it is fairly isotropic, independent of the direction. And the phase windings that I show you indicate that this is a beam that carries unit orbital angular momentum. And so with this, you can repeat the edge detection. So you can send in the image. Again, this is Stanford logo. And you can see the output indeed produce the image. Now, in this case, it's independent of the orientation of the edges. Also, unlike the Christmas tree that I show you for Laplacian, in this case, it doesn't highlight the corner, so you don't see the corner lights up at all. And this is one way to tell that this is not a Laplacian operator. Now, I mentioned the robustness associated with the topological charge. In other words, small perturbation cannot remove the 0. So therefore, this kind of operation actually has quite a bit of robustness associated with it. As one demonstration, it actually has a broadband response. So without changing anything, if you just change the instant wavelengths, you can reproduce essentially the same result. Theoretically, you can show that the bandwidth is easily more than an octave. Here is an experimental visualization. So instead of using a green laser diode, we can use a red laser. And again, you can see that it basically performs almost exactly the same. So this, I think, gave you an impression that one could, in fact, use some of the topological concept to design some of these computing devices in a robust and broadband way. So this concludes, I guess, the first part of my talk, where we talk about edge detection, which I think is a relatively simple computing task, but make connection to quite a few of, I think, quite interesting concepts associated with a variety of nanophotonic structure. In the second part of my talk, I would like now to talk a bit about a neural network. So I showed the slides already. So one of the neural network is this deep neural network, for example, for handwritten digit recognition. And there are 2 modes to operate this network. One of them is something called inference, which is you basically send an image and it make a prediction for you. If you send an image of 5, it predicts that it's 5. And in order for the inference to work, you need to train the network. So the training is done by adjusting the weight or the matrix element of these the matrix vector multiplication until the network produces the correct results. And so the training usually is fairly intensive in computation that require many inference steps. Basically, you pass through this network through a large training data set until it works. So in optics, the matrix vector multiplication, for example, can be done with the use of a Mach-Zehnder interferometer mesh. And so 3 years ago, there's a very nice paper coming out of MIT, Dirk England and Marin Zaliacek, which implement this kind of neural network. So and experimentally demonstrated vowel recognition. And this is a very nice demonstration, but there are a number of aspects that actually one should work on to further improve it. First of all, one of the limitations that they have done regarding what they have done is that they train this network digitally, even though they did the inference in the optical domain. And so what they did is they built a computer model of this network, train the computer model, and then implement the weight of the matrix into their physical device. And this becomes, in fact, quite difficult to do, especially as you try to scale up these networks. It becomes increasingly difficult to build a faithful model if your mesh is too complicated. So it certainly would be nicer if one can figure out a way to be able to take a neural network circuit and directly train it. So in training, as I mentioned, what we do is we need to adjust the weight of the matrix. And in a tunable Mach-Zehnder interferometer mesh, this translates into adjusting the dielectric function in some of the arms of these waveguides. So you would need to figure out a way to really train the dielectric function inside the system. In standard neural network literature, the standard way to train a neural network is what's called the back-propagation algorithm. And in the back-propagation algorithm, you take your training data, you do an inference run, so you pass through this network, and you generate the output, and you compare the output with your desired output to generate a loss function, which is essentially the error signal. After this, you send the error signal back through the network, and this is called backpropagation. And then from there, one can then infer about a gradient on each of these weight matrix. So this is the standard training algorithm. And examining this, you see that the important step here is backpropagation. But this need not be done digitally. You can do that physically as well. What you should do and what you could do is to generate the loss function and then feed the loss function back through the network to do backpropagation. But in the backpropagation, you also need to read out the gradient. In other words, you need to read out how the derivative of the loss function with respect to the dielectric function of each of the points inside the network. And this requires a piece of mathematics, which is in fact very closely related to backpropagation, called adjoint variable method. This method is widely used when you need to compute the gradient of an objective function to a distribution of dielectric function. So as a simple illustration, suppose you were given a computational task, and you put a source here, you put a detector here, and you would like to optimize a structure so that you can maximize the power of the detector. So in a gradient optimization, what you like to do is to compute the gradient of the detector power with respect to the magnitude of the dielectric function at every single point inside the structure. And you do that with two computation steps. In the first step, you do what you usually do. You put a source here, you compute the field distribution, including the field at the detection point. In the second step, you do what's called the adjoint calculation, where you put the source at the detection point, again do the calculation to generate the field distribution. Once you have done that, the gradient with respect to every single point inside the structure, in fact, can be computed by the overlap integral between these two fields. And so this allows you to compute gradient with respect to arbitrarily large number of degree of freedom. So the gradient in this case is an overlap integral, and between the forward field and the adjoint field. And in optics, an overlap integral can be read out by an interference measurement. So what you need to do now is to interfere the forward field with the time reversal of the adjoint field. And therefore, this you can use the intensity measurement to read out this interference term. And that gives the three-step process that we propose to do the gradient measurement. So in the first step, we just send the signal past the Mach-Zehnder mesh, and record the output signal. In the second step, we send the output signal back. We generate the hadron field associated with the output signal, send it back, and then again report the transmitted signal. Now, with this, in the third step, we then take the time reversal of the transmitted field and then beat against the original input field, pass through in the forward direction the structure again, and measure the intensity at everywhere you require the gradient information, and the intensity is directly proportional to the gradient. So here is illustration. So if you take a Mach-Zehnder mesh, and you can compute numerically exactly the sensitivity, and you can also compute it using the protocol that we do, and you see that these two agree. And this is in fact not a trivial agreement, because the algorithm that we propose here, strictly speaking, require that the system is to be time reversible. In other words, it requires that if you have loss, then the loss cannot be modal dependent. And yet, this is an actual physical structure of Mach-Zehnder mesh in electromagnetic simulation. Actually have modal dependent loss up to about 10% or so, but the gradient that you generate is in fact very close to the sensitivity. And that indicates that this technique has sufficient robustness to perform in an actual device. And so here's an example where we use this to train an optical neural network. We give it a task where we were given the red and blue dots as indicated here. And we want to train the neural network to generate a boundary that separate out these two dots. And this, in fact, require that you have a nonlinear system because if you can show that the linear won't work, actually, in fact, cannot generate a contour that's required. So if you do the calculation, you can see that the network actually produce the large contour first before it produces the small contour. The contour is fairly smooth, indicate that it's not overfitted. And also, I think some of the features, for example, that it generate large contour first, actually makes sense if you think about the minimization of the error, how this is done in the system. So now I've talked a little bit about some of the work related to the linear part of the network of the matrix vector multiplication. I would like to also briefly comment on the nonlinear activation part. In this pioneering MIT paper, what they did in the activation is they did it digitally. They detect the signal and then convert to electronic signal, then perform whatever activation function on a computer, regenerate the signal, and send back into the optical network. And so certainly, if you want to build optical network, ideally, you would like to be able to do this in optical domain. Certainly, there are nonlinearity in the optical domain, for example, Kerr nonlinearities and so on. But in neural network, there is, in fact, a strong requirement to generate the specific kind of nonlinearity that you need. And this kind of flexibility is very important for successful development of this network. So with this in mind, what we been exploring is the idea to do a electro-optic activation function. So the idea is that you take an optical signal and you take just a very small part of the signal detected, and then do an electronic transformation of the detected electronic signal to generate a voltage that feed forward to a Mach-Zehnder interferometer, which influence the transmission of the main signal. The nice thing about this is that in doing so, you retain the flexibility of electronic processing, but in the meantime, the signal stay in the optical domain. So recently, in a collaboration with GenXCon, a startup in silicon photonics, we provide an experimental demonstration showing that we can very faithfully reproduce some of the standard activation function that's widely used in neural network, the sigmoid function and the ReLU function. And with a fairly low input threshold, nonlinear threshold in these transformation. And this, I think, is an interesting way to implement nonlinearity with the flexibility that's required to do optical neural network. So in the maybe last few minutes or so, I like to switch gear a little bit and talk about other computational model. Up to now, I've been focusing primarily on this feed-forward artificial neural network. In neural network field, there are other architectures. For example, there's a very important class called recurrent neural network. And this is widely used to process time-dependent data in real time. So you, for example, would like to feed this network in time-dependent data in a sequential way and make decision about the data. As one example, you can imagine training this network so that you will feed it with a real-time stock price, and the network would produce a prediction of what the stock price would be in the next time instance. Obviously, if you can do this well, it's very lucrative. And in what we do, we are perhaps less ambitious. And instead, we would do the more standard example of a voice recognition. So imagine that you speak a particular vowel. So that corresponds to amplitude of acoustic field as a function of time. And you feed this pulse waveform sequentially into a network. And the network generate an output as a function of time as well. But hopefully, this output signal as a function of time is simple enough to allow you to straightforwardly differentiate what exactly is the vowel that has been spoken. So the network that's required to do this kind of computation is the recurrent neural network. And you can open this up, and this is how the algorithm look like. Importantly, given that you are feeding in the data sequentially, the network need to have some memory to remember what the data look like in a few time steps before. And this is done by having a hidden state inside the recurrent neural network. So the hidden state is a dynamic system where you feed the state and you mix with the new input signal and to update the state, but also generate the output, and then you repeat the process. So in doing so, therefore, you create a dynamic system, and then you train the linear part of the dynamic system to produce the right outcome. From our perspective, if you look at these description of the recurrent neural network as a dynamic system, it's actually natural to notice that many of the things that we do on a daily basis, for example, well, theorists do on a daily basis in this field, solving wave equation, in fact, can be read directly as a recurrent neural network. So this is a wave equation. It can come from Maxwell equation driven by a source. Now, you may imagine, for example, put a source in front of a structure and look at the output. So in this case, you can do the source as a function of time of the amplitude and try to get a particular output as a function of time. And this, of course, we do all the time, theoretically. But you can read this off in the language of recurrent neural network. All you do is you basically read the field distribution inside the structure as your hidden state. This equation then gives you the hidden state dynamics as well as the mixing of the input to the hidden state. And the output, of course, is directly related to the hidden state. And in this case, if you have a wave velocity distribution inside the structure, then you can think about training the wave velocity distribution, for example, refractive index distribution, to produce the correct outcome. So in doing so, you can map the wave equation into a recurrent neural network. And this allows you to take the machinery that people have developed in training recurrent neural network to go train a differential equation. And so here's an example to do vowel recognition. So what we would do is we put a source here and input into the source an input waveform that corresponds to different way that people speak the same vowel. And then we train an area here in terms of its velocity or index distribution, so that if you speak A, it would route the signal in one point. If you speak E, it will route here. If you speak I, it's going to route the signal here. And this is done in the training algorithm by sequentially adjusting the index distribution inside this region until it works. So we start with a structure that is uniform, and then we train it until we get a fairly non-uniform structure that actually performs the functionality that's required. So here's some detail in the training process. To characterize a recurrent neural network, a typical tool is something called a confusion matrix, which basically says that if you input a particular vowel, you look at the prediction of the output, and you would like the network to be able to, for example, predict that it is what you have spoken with 100% probability. So you can put this in a 3x3 matrix. Then what you would like to do is to get a matrix where the diagonal matrix element is 100% and the off diagonal is 0. And so before the training, in fact, the structure, which is uniform, does not work for bizarre reason, which I'm not sure I understand. When we put in at, it always think it's E, so which is kind of weird. But if you train it, then it actually works very well. You can see this both on the training data set and on the testing data set, that it's strongly dominated by the diagonal matrix element. So which indicate that this actually works. And this is an image of one simulation where if you speak one vowel, the power get routed to one point. You speak another one, it get routed to the middle point, and so on. So you could actually see visually that a complicated looking structure, it in fact behave as a recurrent neural network to perform the vowel recognition that we desire. This is in fact a rather non-trivial processing task. One way to see, I think, is to just take a look at the typical spectra of these three vowels that we do. And you can see that, in fact, they very strongly overlap with each other. The spectrum of the three vowels actually looks fairly similar. So at the very least, this is not a spectral filter to try to get the information out of these waveforms. So I have mentioned quite a bit about the connection of wave physics to recurrent neural network in terms of the fact that you can formulate wave physics in terms of recurrent neural network. But there are also unique aspects of these wave physics recurrent neural network that are in fact different from standard recurrent neural network. And here is a representation of the wave physics recurrent neural network that I talk about in the form of a recurrent neural network. So you have a box here, you have a hidden state that going through. One thing is that the matrix that's involved in this is a sparse matrix rather than the dense matrix that's commonly used in recurrent neural network. So the memory capacity of the hidden state in this case, the state need to propagate through the structure. So the memory capacity is in fact directly proportional to the size of the structure. Also, these are physical dynamics, so they are constrained by energy conservation. And this is in fact interesting because it may in fact be useful to overcoming the divergent gradient problem in the training of conventional recurrent neural network. If you have a arbitrary dynamics, it's actually difficult to prevent the dynamics from going either exponentially exploding or exponentially decaying. Whereas physics provide a way that you are always training in the subspace that the system would not blow up. So I think this is actually some of the interesting aspect related to this concept of wave physics recurrent neural network that I think is probably useful to further explore. So with that, let me briefly summarize. So what I hope to convey is that there are actually interesting opportunities in thinking about using optics to do either relatively simple or fairly complicated computation. And this is, in recent years, I think certainly, as I mentioned, this has a long history, but the resurgence of this idea is related to many of the new opportunities and challenges associated with neural network computation, and also allow us to utilize many of the new optical physics that are being developed in compact nanophotonic structures. So with that, let me stop here and thank you for your attention.
Thanks for the fantastic talk. Do we have any questions?
Oh,
I have a quick question, if that's okay.
Yes,
Sure.
please introduce yourself.
Yeah, so I had it's kind of two questions. One's a little more direct, and one's sort of speculative. So the first question is about your your wave recurrent neural network. It's a really cool idea that you train the optical medium directly. But I was wondering if you wanted to comment on the different approaches taken by people like Sylvain Guigan and Carlo Conti with their reservoir approach to recurrent neural networks, where instead of, say, training the optical medium, they leave the optical medium as is, but train a linear set of weights on the output to do classification tasks. And I was wondering if you saw any advantages over training the medium itself to create a sort of recurrent neural network.
Right. So it's a very interesting question. I think that it seems like the recurrent neural network architecture is, if you forget about the physical implementation, just look at the algorithm, it's more expressive than the reservoir computing architecture. It seems like that's the case. Now, the reservoir computing architecture is very interesting because it really directly tailor into optical structure, because you just need to basically generate a relatively complex linear optical structure to do it. But I guess from my reading of the literature is that it's not as expressive as the recurrent neural network.
Okay. And if you'd allow me, I have one more question, which is sort of a little more speculative, which is in the hardware neural network community, and it seems especially people who are working in recurrent areas and reservoir computers in particular, there seems to be a sort of discussion about this idea of the edge of chaos, that if in your hardware system you have some traces of chaos, and you operate on the edge of that, it has more computational power. And people seem to be split about whether this is necessary or true. And I wondered if you had any thoughts on whether you guys use chaos in your work, or if you think it's necessary to have a highly powerful sort of hardware neural network computer.
I should say that we have not looked into this particular aspect very carefully. So I'm not sure I can easily comment on it, but I think it's a very interesting observation that people have made about the reservoir computing. Certainly was very interesting.
Okay, thank you so much. It was a great talk.
Thank you.
Do you have other questions?
Yeah, can I ask a question?
Yes.
Yeah, so how about the acquisition speed of your optical edge funding method? So does it beat the digital edge funding in all the aspects? Like the resolution is really high. You mentioned 7.5 micron. How about the acquisition speed?
In this case, so I would say that in this case, all we do is we take an input field and pass through a structure. And the structure in this case is just an interface. For example, in this particular case, is an interface between silica and air. So we really didn't do much. So in terms of generating this image, it took essentially 0 time by almost any electronic standard, because it's only the time that it took to reflect from a surface. And that's probably femtosecond scale. Now, at the end of the day, though, I think one would still, what we envision that this could be interesting is probably as a front end of a image processing network. So many of the things that you would do on the electronic image processing side will still follow afterwards. So this does not go all the way through.
Yeah, thanks. And just curiosity, do you have a plan to commercialize this?
So we did file patents about it. So we did that. We have not commercialized it.
Yeah, thanks. Thank you for the great talk.
Do you have other questions?
Judy, I actually have one question.
Yes, please go ahead.
Yeah, Professor Fan is really a great talk. So I have some questions regarding the neural network part. I know there are 2 startups trying to commercialize this group, this technology, right?
Right.
So
at least 2, yes, yeah.
Yeah, at least 2, yeah. So I know people from the machine learning background, they have concern about the photonic approach, because first of all, about the how we can reconfigure the neural network. That's one problem. The other is, so this is probably a physics limitation, because photonic devices are generally much bigger than electronic devices. So in terms of computation density, so photonic neural network is much worse than electronic ones.
Mm-hmm. Yes.
So that's another concern. And also, it's true that the light can propagate through the structures with picosecond time scale, but in the end, we still need to do ADC, DAC to convert it into digital domain instead of in order to do further processing, right? So can you comment on that? So can we really realize that it's a fair argument that photonics can compute with picosecond time scale?
So I will address the last part. The way that we do these electro-optic activation function is precisely to try to avoid doing full optical detection into electronic domain and then do it and then regenerate.
Mm-hmm.
The ACDC, the A to D conversion that you talk about is precisely try to avoid that. And I think that pathway seems to be doable. In terms of, you can think of, in fact, many challenges of these optical neural network. There's a long list of it. I would say that reconfigurability is probably not high among the list that I worry about, because for these Mach-Zehnder meshes, reconfigure one certainly has been done before. You can bias the waveguide. And if your goal, and I think most of these machines are going to, in the end, be used for inference purposes. So the speed of the reconfiguration is probably not a major concern.
Yeah, so for example, for standard MNIST data set, normally people have tens of layers. I mean, it's hard for me to imagine that we have tens of chips that are fixed, or I mean, people have to do some reconfiguration, right?
Right. Yeah, and I think that I don't think is a major issue, because reconfigurable silicon photonic chip certainly has been done, I think, in the academic side extensively. Mm-hmm. I would, in my mind, one of the issue that I can think of was that is the scaling up issue. Mm-hmm. Right? If you do minutes, is 768 pixel. And I don't think there's any plan to build 768 waveguides.
I see. So in your point of view, still that the scalability of photonics is the main issue to really, okay.
Yeah, it's an issue. So for example, some of the free space idea associated with matter surface could be very interesting.
I see.
Because there you can do very large matrix vector multiplication without much of an issue.
Right.
Also, I think even if you have a very small processor, let's say you have 10 by 10 matrix, if you think about how computer do computation, if you will ask computer to do 1,000 matrix vector multiplication, it's not like the computer actually load the entire matrix into the CPU or GPU.
Yeah, but normally GPU they can do, for example, the TPU they can do like, I don't remember, hundreds by hundreds, right?
Right, but my point is that, well, let's say be more ancient and talk about CPUs and so on, which are not specialized for it. But the actual computational core in there to do the computation actually is relatively small.
Yeah, that part I agree with you, but then it's related back to the reconfiguration problem.
It's not necessarily reconfiguration problem, because you can imagine, well, it is related to reconfiguration, but it's also related to how you program these things. Yeah, how you program. So I think, in other words, my view of it is that, like I said, I can think of a very long list of challenges associated with this.
Definitely,
and I think there are also many interesting ideas that one can pursue.
I see. Yeah, thank you.
Do we have other questions?
Definitely. Should we still introduce ourselves?
Yes, please. Yes.
Fantastic talk, by the way. I'm really interested in bridging optical sciences and neural networks. My master's was in machine learning, so this is just very cool to hear.
Thank you.
I just had some questions. Actually, first comment, very clever on the back propagation, doing it out of the computer. And I was wondering, for managing your nonlinear functions, because I don't know if you can go to that slide when you were showing the circuit.
Okay. Yeah. Yes. Maybe this
one
one's
more.
better.
Yeah.
Easier to look at. Yeah.
This is is it still a digital circuit managing the nonlinear function?
You can do either one. It does not matter. You can do digital circuit, and I don't think we did digital circuit in our own little work on the experimental implementation, but you can do either one.
Okay, cool. I wasn't sure if it was. I was going to ask if it was digital, if you'd observed any like flooring in the air just due to the discrete nature of it being digital.
Right. I don't think we did digital. You don't need to do digital circuit, but you could certainly because the point is that you detect so let me make sure I got the point across that this is generating nonlinearity, right? So you would like the transfer function to depend on the intensity of the input signal.
Right.
So what you do is simply to detect so that you know what the input signal is.
Right.
And from there, you apply a voltage to here. So whatever convenient thing you do. So this is not to digitize necessarily the input signal, as long as you have enough signal noise ratio to know what the power in the input signal really is.
Cool. I thought maybe the transfer, how you were managing the transfer operation was digital. I guess another question I have is let me think. Oh yeah. When you were doing the time-dependent recursive neural network, optically, how are you storing the latent space?
Yes, it's actually just a field distribution inside the structure.
Oh, I see. So
you see that you have the source here, and that generates the field, right? Now, when the source changes, the next instance of the field depends both on the source variation as well as the field that's already inside the structure. So that's the hidden state.
Is there a delay in, I guess?
Yes. So that delay is, there's a memory, right? Because there's a size of the structure and the wave then leaks out. So
I see.
So
I see.
is a time window associate with the so we are not storing the entire pulse into the structure.
Oh, okay.
Yeah.
So I guess physically, how are you storing it? Is how I'm trying to imagine it.
Physically, it's just the wave amplitude distribution inside the structure.
Oh, I see.
Yeah. And this is entirely analog. As a user, you don't need to know.
Right.
Right. But that's why it's called hidden state, right?
Right.
You see input-output function is hidden from a user's perspective.
Awesome. How did you get this imagery? I guess you're like physically peering into the
right. Yeah.
The system.
So I can know, right? I simulate the thing, so I know.
Right.
But as a user, you don't have to know.
Very cool. And I was looking at this data. Have you guys thought about instead of mapping it to vowels, maybe mapping it to the, what are they called? The phonemes for words. So figure out why you get that 100% there.
Right. Yeah. So I think there's a lot to be done. For example, this is a very, I would say, a simple task, right? It's only 3 vowels and so on, to understand how these things scale up. And what exactly is required to do a more complicated task in these systems. I think there are a lot of open questions that we haven't done yet.
Very cool. I'm really excited about the part where you were talking about the doing the back propagation on the board itself.
Okay.
And I guess the way I was thinking about it, I guess there were some questions about reconfiguration. What is, I guess, like in my head, when I think reconfiguration at the hardware level, I'm thinking like FPGA. But what is the limitation with reconfiguration for, I guess, what people are asking about? What are people thinking?
So maybe let me make sure that I first say physically how you do reconfiguration in these systems. So the black line here are some silicon waveguide. And what you are controlling is the refractive index of the silicon waveguide. As one of the slowest way to do it. There are faster way, but the slow way is easier to understand. You put a pad on top of the waveguide, and you adjust the temperature of the pad.
That's how you tune the phase.
Yeah, that's how you tune the refractive index and influence the phase. So that's the slowest way to do it, but it's not the way to describe. There are also electro-optical way to do it. But so therefore, at optical layer, that's the control that you need. So that translates into changing the temperature of each of these pads. Then you imagine that you can build circuits to control these temperatures.
I see. I guess I was thinking, could you have you thought about generating like a fully connected system and then opening and closing channels? So for that, is that what people meant also by reconfiguration?
You could do that. I guess what you mean is, for example, like this drop-off kind of idea where you remove some of the nodes in the network and those kind of things. That you can certainly do with these kind of reconfiguration. It's not that hard to do that kind of manipulation.
I guess like what you've proposed here, I'm imagining like a very awesome platform to do your training on, and then go and manufacture these things. You know, like you would maybe a FPGA.
Yeah,
the chip, I mean.
Yeah, in a way, it's very. There is quite a bit of analogy that you can make in that way. Yes.
Wow. Cool. I guess I don't know. Maybe I'll wait before I ask more questions. Let people get a chance.
We have other questions?
Yeah, can I ask one more question if you don't mind?
Yes.
Yeah, so 5 years ago, you were talking about the radiative cooling at Fudan University. So I'm just wondering, how did that project go? Like,
well, it's interesting because I thought about talking about energy, and in the end decided not to talk about energy. I obviously have an hour talk. If necessary, I can give. That's been going well. It's really getting scaled up to an extent. I think we have a company that was really trying to put that on the roof of supermarket and really taking a lot of data and so on. And a number of other people have started companies that are that are doing radiated cooling. And in fact, I would say that these days it's becoming such a large effort that there are enormous number of different materials that people have discovered that can do radiated cooling that I don't think I can keep track of it anymore.
I see. Yeah, thank you. Those are very impressive.
Great. Do we have other questions?
I have a question.
Yes.
Thank you for the talk. I had a question or a curiosity about the neural network portion of your talk.
Mm-hmm.
Is the work being done, or do you envision work being done in the optical domain to improve security, I guess, over fiber communications? So implementing a sort of signal detection or filter from an optical neural network standpoint into already existing fiber networks to improve security, or do things in that domain, or as a possible application for this emerging technology.
I think it's an interesting idea. I would say we have not thought much about it, but I think it's a very interesting direction. One of the advantage of doing signal processing this way is that you are doing signal processing in the native domain of the signal. And so I think it's interesting. If you have a reference or two, I'll be very happy to take a look at it.
Great, thank you.
Do we have other questions? So if not, we can switch to the meet and greet portion of the talk, which is mainly for students to introduce themselves and ask you questions that are maybe not necessarily technically related to your talk.
Okay.
So do we have any students that want to take this unique opportunity to introduce themselves to Professor Fan and ask a question, perhaps? If not, I can start with my traditional icebreaker questions and see how it goes from there. Sometimes they're very shy. So my first icebreaker question is always, what's the next big thing you would like to see someone else other than yourself work on?
That's a very good question. The question is, why wouldn't I work on it? I think actually, in terms of fundamental concept side, I hinted at here about topology. And I think conceptually there are a lot that can be done in optics and in figuring out robust ways to do things. That is something that internally we're very excited about it. Is probably, I'm speaking out of my immediate reaction about things that I perhaps is one of the areas that I think could be extremely rich. Historically, when people think about topological photonics, the standard way to think about it is think about one-way edge mode. Think about modes that backscatter immune and like a quantum Hall effect. Those are certainly very interesting, but I think there's a much broader context where topological concept can be used. And I'm giving an example here where you can do some computing with it. And I think there are maybe a lot of interesting opportunities that one can think from a more basic point of view.
Other students who want to introduce themselves? If not, I can go with my second question.
I'll try again.
Okay.
Hi, my name's Kevin Chu Figueroa. I'm a master's student here, studying optics. I guess, have you thought about, other than nanophotonic structures, have you thought about other optical phenomena to use for your layers in your network? Like refractive maybe, or,
in fact, I really didn't have to mention the optical neural network has a very long history. Mm-hmm. In the 80s, there are outstanding work by, for example, Dimitri Sautis, who are building a wide variety of neural networks using holograms and using diffractive optical structures. And I think you should check those papers out. Those are fascinating read.
How do you spell Sautis?
P-S-A-L-T-I-S.
Oh gosh, P-S.
P-S-A-L-T-I-S. I hope I didn't butcher his name. This is on record, so.
Gotcha. Hopefully autocorrect will help me out. Yeah.
Yeah.
Have you seen much in refractive, like maybe freeform?
Yeah, that could be very interesting as well. I think it would be interesting to examine those. Some of the difficulties, I would say that there are a number of difficulties associated. One of them, obviously, is that it's not a very compact structure. Many of the experiments occupy a table.
Yeah.
And it's very difficult to imagine. And this is why some of these integrated photonics approach or matter surface approach are interesting, because you could imagine this to be an actual device, right?
Right.
Rather than a experiment occupying somebody's table. So I think this is one of the issue that, and that connects to the development in the past few years of past 20 years of nanophotonics in that sense. That I think really put in the new opportunities in this field. But on the other hand, it is true, and it's fascinating to read that many of the concepts that we are talking about now, you can find interesting precursor in those literatures as well.
I guess I'm thinking about adoption of these inference systems, and I think if it's going through like a diffractive filter. I'm not sure I can still, as a human being, interpret the information on the image sensor versus, just explainability, I guess. People can tend to be skeptical as it is about machine learning. So I have experienced that firsthand towards me. So I was just curious, like in terms of adoption, what do you think is popular for inference going forward in the future? I guess where do you see the research going?
The practical side of research, I would say, is really to construct some of these networks and scale it up. Is the practical side of the research. I would say also, I actually come from a theory and therefore a more fundamental perspective on many things. I would say that it opens also the kind of question on other levels. For example, I mentioned about these recurrent neural network and how one really can understand, it's probably too strong a word, but how one can say something about these complex structures that we see. Right? They can certainly do strange things. What are the essential elements of these structures that one can understand them a little bit? What are their properties? I think one of you mentioned the edge of chaos in the reservoir computing, which is a very interesting, I would say it's a very interesting hypothesis, actually. I don't think it's fully proven, but that's a very interesting hypothesis. So there are, I would say in that spirit, there are many interesting basic questions that one can ask as one look at these increasingly complex structures and systems.
Cool. I think I'll take a break again in case other people have questions.
Masood, please.
Hello. Yeah, good to see you.
Hi, Shanhui. Good to see you. Very nice talk. Thank you.
Oh, thank you.
Well, these neural nets, the way they are implemented today, the information always flows forward. Of course, you do the back propagation to correct the coefficients, but the information always goes one way. Now, in optical system, you can always have a scattering or back reflection. So is there any kind of feedback mechanism that first one has to avoid, or if it's unavoidable, one can use it to advantage?
So the one that we do here is, in fact, like what you say, where you have a very, very complicated multiple scattering. So that's one way to do recurrent neural network. It's not explicit, it's implicit, meaning that the hidden variable is the field. And of course, the field bounces back and forth in the structure. You can make this explicit by constructing explicitly a network where you feed the information back to form a loop. And I think there are interesting work that people have done. I think Marin Saliaci at MIT, for example, have an interesting paper looking at constructing recurrent neural network that way. So I actually agree with you that it is a very interesting opportunity in optics to look at these multiple scattering, to look at these recurrent or feed backward network, because it's so natural in optics. And that's part of the reason we look at here as well.
Okay. All right, thank you.
Do you have anyone else who would like to introduce themselves? Not one.
Hello.
Okay, Kate.
Yeah, this is Kane. So I'm a fifth year PhD here working with frequency combs. So 5 years ago, I was working with Professor Lei Zhou at
yeah, I know him well.
Yeah. So I have a question about the coherent icing machine. So right now, a lot of people are talking about that to solve the P and NP problems.
Yeah.
Do you have time to work on that, or have some comments for the coherent icing machine?
It's a very ambitious program. Certainly, one of my he's a former colleague now, but Professor Yoshi Yamamoto, who is in the same building as I am, did outstanding work using OPO, right? Parametric oscillator. I think it's a very interesting idea to go after those problems that are truly computationally hard in these kind of analog computing fashion. And I think it's a very ambitious idea. I do not know at the moment, and I could be wrong in this, I do not know at the moment to what extent this kind of approach has outperformed conventional digital computation.
Right.
So in this sense, I think the neural network stuff is in fact far less ambitious. This is certainly not the doing the true computational hard problem of computing, but rather maybe to look for some of the unique advantage of optics that can speed up part of the process. And I think both of these work are interesting. One can take their pick on how ambitious they want to be.
Right. Yeah, because last month I attended a conference that's the NTT research held by Yamamoto.
Right.
So there's one day, I think day one, everyone is talking about the coherent icing machine. And it seems very challenging and hard.
Yeah,
thanks.
So do we have anyone else who wants to introduce themselves? So
I have another future question. What are your thoughts about the future? I guess every time I see a new type of neural network or architecture, you see lots of different goals or optimization goals. In terms of this kind of architecture, I guess I'm thinking about, as you mentioned, right? It's less about tackling the heavy computationally non-trivial problems versus the rapid execution. In terms of rapid execution, then tuning the phase, like let's say you have an adaptive network, what is the response time for something like that?
So I gave the slowest example I can think of, which is a thermal optics field tuner.
Is that pretty slow?
That's pretty slow. I think we're talking way slower than megahertz.
Oh, okay.
Yeah, probably even slower than that. Electro-optic, which inject carriers into the waveguide, people have done a lot of work. And those you can probably get to gigahertz scale.
Wow.
And that has been demonstrated. So, in fact, if you think about it, this is how people send data anyway, right? It's electro-optic modulator that encode the electronic data into a fiber, right?
I guess
that's usually at the gigahertz kind of scale. So that kind of speed is probably maybe even 10 gigahertz. But in any case, that's the kind of speed that I usually keep in mind in thinking about these kind of approaches.
Have you thought about what? I guess people start looking into that more. What inherent trade-offs they might run into?
I think for electro-optic kind of setup, this is probably probably 10, or if I stretch it to 100 gigahertz or something, is probably at the edge of what you can do already.
I see. Oh, I meant like maybe less spatial resolution on the device, or I was just trying to think of what inherent trade-offs might be versus like manufacturing versus having something adaptive.
Right. So maybe my answer to that rather is to say that there are, I would rather say that there is a range of things that people can easy, probably the wrong word, readily do. For example, modulation up to 10 gigahertz or so, build modulators that are on the order of, if you want to do micro ring resonator, build modulator on the order of tenths of micron size, and with a particular kind of insertion loss that one can talk about. Those are the set of things that can be done. And I would say from an academic point of view, straightforwardly done. The spec beyond those are actually difficult.
Yeah, I mean,
The
sounds
spec
pretty
beyond
high
those
as it
are
is.
difficult. Yeah, it's high, but the spec beyond those are difficult. So what I would say is that within those spec, it is in fact possible already to do a lot of interesting things on the neural network. I'm not saying reaching that spec is necessarily trivial, or integrating, generating large systems, having those spec is trivial. No, none of those are. But I think within that confinement, there are already a lot of interesting ideas that you can pursue already.
I guess those
are things that people can manufacture.
I guess I'm thinking like historically, right? With every new technology, there's always limitations that run up down the road, and same with neural networks and machine learning. Yeah. Do you think, I guess, like in the next 15 years, what do you think is the limitation people are going to run into with this? It's not necessarily a bad limitation. I'm just thinking.
It's not necessarily a bad limitation. What I would rather say is, in fact, this is a unproven technology.
I see.
Yeah. So in fact, there's a lot of unknown of what the true potentials are. I will actually take that view.
Right. It's not clear what the potential is, nor is it clear what the
limitations
constraints.
So, I think there's a lot that actually is difficult to, without doing it, to truly extrapolate. It's not at that stage yet.
What do you think needs to be done then, going forward?
I think I need to try it. I think people need to try more, and to build it up, and to scale it up, and to really innovatively look at problems or even algorithms that can be done in these systems. These are highly specialized hardwares.
Yeah.
Right. It's not, as I'm hopefully gave the impression that this impression is implicit in what I'm presenting. I talk about optics for computing, but these are highly specialized computation. It's not for general purpose computing at all.
I guess my thought then is, in order to tackle these specialized problems, then maybe the next step is collecting lots of this specialized data.
So I think it's to identify some of these opportunities that people are already thinking about.
I see.
Yeah, you can see
where data is already available. Yeah.
Yeah, and to push forward, because I actually think that many of these ideas are at a fairly early stage at this stage.
Well, early and very exciting.
Right. So there's if you were to start a company in this, you could easily say a lot of risk as well. In other words, it has not been, if you're starting a company, I don't think that's been fully de-risked.
Mm-hmm. Oh, you said fully de-risked? Oh.
Yeah,
Oh.
as some of these people like to use that term, right?
Gotcha.
Whether you have developed the technology to be mature enough that most of the technical risk has gone away. I would not have said that for many of these technologies.
I see. I'm like, yeah, I mean, it's hard to predict what the risks will be when they haven't been experimented yet.
Right. Yeah, many of the things are, I think, in my mind, actually are wide open.
Well, to someone interested in this stuff, do you have any course topics you recommend signing up for students?
Yeah, I'm not sure there's a good, certainly there are papers you can dig in. That's
right.
probably so maybe we actually have a review that came out. I think it's today, actually. I forgot to put a reference in Nature. This is a whole bunch of people, about 10 people, written a review on optics for inference.
Oh, cool.
So that probably gave, I think it probably, you should check it out. It would give both a historical view, but also some of the broader view, certainly much broader than I talk about here, on where the state of the arts are. So you probably can check that paper out.
Well, two questions. One comment, one question. Congrats on Nature. And two, do you have the DOI or the title?
If you send me an email, I'll email you.
Cool. Thank you.
Great. And so our final question for Professor Fan, what is the best advice you have for graduate students?
Well, I would say that to think about big problem, but to do what you can.
Great. So thank you so much for speaking to us today. We really appreciate you taking the time, and it was such a fantastic talk. Thank you.
Well, thank you, Judy. Thanks again. I also enjoy all the interaction. Thank you for arranging it.
All right. Yes. Thank you very much.
Okay. Yeah. Bye.
Thank you, Professor.
Thanks.